All right, so this is going to be the recording for Traits and Reproduction 1.5. And you can see I'm already into the assignment for today, which you can find on our homepage like always. Today we are going to look into more of how proteins will affect how the trait is made. So different proteins make different traits. And one cool little side note that we're looking at today is a protein that's nicknamed the sprinter's gene. And it's also called the speed gene. There's a few nicknames for it, but its scientific name is ACTN3. And so what this gene is a gene that a lot of the most elite and fastest runners have. And so they're trying to say that having this gene will make you have a very superior running ability. And so we're going to kind of look at that a little bit. But going back to the activity, looking at the warm-up, you can see here that we have this family tree that we've seen a few times, but this time we're going to notice that they have proteins here at the bottom. Looking at this question, they are telling you that the medium silk flexibility is the most desirable, and so that silk can be used for a lot of medical purposes. So they want you to answer the bottom question, why do you think offspring B has the medium silk flexibility trait? And so the idea that they really wanted you to get is that each parent passes down one trait to their offspring. And those traits can obviously be different because you have two genes for each trait. So eye color, you have two. And so each parent has two, and they each pass down one. So there's a lot of different combinations that can happen. And we'll go into a lot more detail with that concept. So if my parent one has low silk, it would have two connectors of 4. So just like this one down here, it would have 2 of the proteins with 4 connectors. And then my mom over here would have a medium silk flexibility, which I can see from offspring B would be 1 protein with 4 connectors and then 1 protein with just 2. And like I said, the idea is that each offspring is got one trait for the parent. So for my offspring male A here, it would have gotten 1 of the 4 connectors from the dad and then 1 of the 4 connectors from the mom. For my offspring B, which is our female, same thing. It would have gotten 1 4 connector from the dad, and then it would have gotten this 2 connector from the mom. Same thing with offspring C. It's got low silk, so it got 1 4 connector from the dad and 1 4 connector from the mom. For this is kind of a weird one. We see that there's the same 2 connector, but then we have this random no connector. And that is where we come in with dominant and recessive traits. And that is a whole other topic we will go into more in chapter 2. But just hold on to the idea that one trait comes from each parent. So, moving on, there is a few little activities that you're going to do today. You're going to use a simulation for some of them, and then we're going to look at that ACTN3 protein I talked about in the beginning. So for the first part, you're going to see that this is back. You saw this already earlier in the chapter. So the chapter question is, why do traits for silk flexibility vary within this family of Darwin bark spiders, which is that image you just saw? And the idea here is we have 3 claims, and obviously one of them is correct. So claim 1, the offspring have mutations that affect their traits. Claim 2, the offspring's traits depend on which parent the offspring receive more traits from. And then claim 3, the offspring receive different combinations of traits from their parents. And so now that we're wrapping up chapter 1, I wanted you to type here which claim you agree the most with at this point, and then tell me why. Just a quick sentence why. And then you were going to open up the simulation and you're going to use the simulation to investigate some of the spiders and the different traits that they have for different features. And I will show you a little example of that. Well, so while that loads, let me show you this. So you're going to notice that you have 4 boxes. So we have box 1 here, which is looking at the spider Greg and looking at his feature of silk flexibility. And then we're going to look at Greg again. And then Ruby, we're going to look at her body color. And then Otis, we're going to look at stripe color. And for each one of these 4 boxes, you're going to do a similar procedure. So you're going to go to your simulation. And log in and all that jazz. Okay, so the first box has Greg and it's looking at silk flexibility. So you're going to start by clicking the feature. And so like you did Otis, stripe color, Ruby body color, you'll click on the feature and then the spider. So I know that I have Greg and I see that his trait for the his trait is low flexibility for the feature of silk flexibility. Oh, it's been a long day and it's only 1 o'clock. So I'm going to go back to my document. And so for your observations first, you're going to tell me what the trait is. So Greg has low flexibility. And then you're going to look at the protein for that trait. So you will go back and see that inside Greg's cell, he has all protein 1. And so you'll go back and say that he's got protein 1. And then you're going to make a prediction. So if you added more protein 1, what do you think would happen? And so you'll predict and then you'll test it out. And how you add those in is you can literally drag and drop right down here and add them in and observe what happens. And you will follow that same procedure for all of your different spiders. And the whole idea that you're supposed to get is that we can see different proteins are making up those different features. And then we have our ACTN3 protein down here. And I had you all do this in groups, but if you miss class, you're just going to have to do the 3 groups on your own, all 3. But it's not too much. The idea is that they ran a test to understand if this ACTN3 protein actually does affect running ability. And so the test that they did was they got a group of runners and measured the protein amount they had. And then they had them participate in a sprint and kind of compared those results. And so group 1, the scientists found that runners who were the fastest had the highest amount of the ACTN3 protein. So what it wants you to do down here is tell me if you think that the amount of that protein, if that evidence helps prove that the protein affects the running ability. And then group 2 had a different piece of evidence. So each group has a different piece of evidence that came from the test. And you're trying to say if each piece of evidence supported that the ACTN3 protein affects the running ability or not. Excuse me. So group 2, the evidence is that scientists found the runners who ran at an average pace only had half the amount compared to those fast runners that were mentioned in the first group. So the average pace only had about half the amount of protein as the fast runners. And then the last group pieces of evidence was that scientists found the runners who were the slowest had no ACTN3 protein at all. And so do those 3 pieces of evidence support the fact that we think that this protein affects running ability or not? And I showed a clip that had to do with Olympics and how they find that nationalities come into play because of location and just like genetics and passing on the traits from families. And some of our families are from different parts of the world. And I guess there's certain parts of the world who have more of this protein in their genetics than others. And so we usually see a lot of the same ethnicities doing better in different events in the Olympics and things, depending on if they have this protein or not. And so I showed that little video clip. It was just an extra. It's not necessary to get the lesson done, but I just kind of wanted to add that in because I thought it was interesting. But that is that. So make sure you get all this done and turn that in. And then, as always, the notebook page is at the bottom here for you. These important ideas are there to kind of summarize the lesson and the key points.